Dear students, this is Anup, a course instructor of Principles of Communication System for 5th semester B section. Welcome to yet another online tutorial on Principles of Communication System. So in previous session, we tried and set a context for this entire course, that is Principles of Communication System. Wherein we tried to discuss the need for modulation. We even have seen how modulation can facilitate multiplexing of various information through a single channel, and we also saw how modulation can reduce the height of the antenna and all those aspects, right? Apart from that, we tried to have a overview of various frequency bands used in communication and their applications, right? Also, we have discussed about a typical communication system and its constituents, and further we discussed about the most important aspect of communication, that is modulation, its classification, and the different types of modulation schemes which we'll be addressing in this particular course, and other topics which will come under this course. That was the discussion of our previous session, right? So in this session, we'll straight away start with amplitude modulation, which is your module 1, right? So in this particular video, I will be discussing about the basic definition of modulation and amplitude modulation. And before we proceed further, I would like to set the context as why we should learn the contents in this particular module, the motivation behind learning these different topics. Basically, we'll study about different mathematical modeling and modulator and demodulator, and maybe and by discussing the types of AM and by giving you a big picture, we'll try to find out the motivation, and further we'll discuss the mathematical modeling of standard AM, and I'll conclude this video with an illustration of or the effect of modulation index on the modulated signal envelope. So that is the plan for this very short video, right? So now, to start with, as you all are aware, modulation is the process by which some characteristics of the carrier is varied in accordance with the modulating wave, and as per your textbook, the amplitude modulation is the process in which amplitude of the carrier wave is varied about a mean value linearly with baseband signal m of t. So I believe it is actually what a complete definition for amplitude modulation, right? It says amplitude of the carrier. So this is the carrier. Normally we'll represent carrier as C of t, and it will have a frequency. It's a sinusoid of frequency fc, right? And we'll represent our message signal as m of t. This m of t will be a baseband signal. By baseband signal, I mean it will have a frequency contents from 0 to a maximum of W hertz, and the spectra will look like this. The spectrum will have both positive and negative frequency contents, right? About the spectrum and about negative frequency contents and all those aspects we will discuss in detail later, right? But for instance, you should you please accept that the baseband signal or baseband information signal spectra will be something like this. It will have a maximum frequency component of W hertz starting from 0 hertz, right? And as per the definition, right, the amplitude of the carrier wave should vary linearly in accordance with the message signal. When I say linearly, it is obvious that the amplitude should not vary in a proportional to square of the message signal or into any other power of the message signal. It should vary proportional to the message signal, linear. So you can see the variation in amplitude, it is linear. The variation in amplitude here, it is exactly accordance with the message signal. If you see here, the variation is exactly proportional to the message signal, and also you can see this variation is around a mean value. For instance, in this case, if we assume the carrier amplitude is equal to 1, the modulated signal amplitude is varying around this mean value. You can see this dotted line. So that is what the definition says, and you can see this is also a type of modulation. But if you see this envelope, there it's somewhat distorted. So there is some problem with this actually. What at these points actually there are some problems. What leads to that problem and why that problem, all those things we'll discuss in the coming slides. But now I think you are pretty much clear with the definition of amplitude modulation, right? But merely knowing definition won't help us to actually what analyze the nitty-gritties of this modulation techniques, right? So what we should know is we should do a detailed mathematical analysis. But why we should go for that? That actually what is what you should initially appreciate. So for that, I'll try and discuss what we will learn in this particular module and what is the motivation behind those topics and all, right? So before we move ahead with that, one thing which you have to keep in mind is, right, if you consider any communication system, bandwidth and power are two most important resources, right? We should try to utilize minimum bandwidth and minimum power as much as possible, right? So there are many reasons. Maybe one simple reason which I can tell is actually if a single user is allocated more bandwidth, right, then what happens is the number of users that can be accommodated in that particular system, or number of users to whom a service provider can provide service will be less. So individual users should use minimum bandwidth as possible, right? And also power level, right, while transmitting we should transmit the minimum possible power level. So there are many reasons for the lower power level transmission. One of them is actually what the interference it will cause to different systems or the same system. And one more thing is exposure to very high electromagnetic radiations. It is not desirable for the living beings in this planet. So that is also another. So because of many reasons, bandwidth and power are two most important resources or scarce resources in any communication system, right? So that is the key point which you should remember before we move on to this discussion. So we'll start with standard AM. So amplitude modulation, right? The key attraction of amplitude modulation itself is it is the most simple modulation scheme which we can implement, right? To generate and detect it is very easy, and out of different types of amplitude modulation, this standard AM is the simplest one. It will have actually what the least transmitter and receiver complexity, right? So you may be wondering what actually is this. You don't have to bother, right? So here I have shown spectrum of a standard AM signal. This is spectrum of standard AM signal, and this is spectrum of a message signal, M of F, right? So in detail we will obtain the spectrum later, but now if I have to comment on bandwidth and power level, I should make use of the spectrum. That's why I'm using this. You don't have to worry by seeing this spectrum, right? So this is our message spectrum. So this is a baseband spectrum. So you should remember this is a baseband spectrum. It will have frequency component from 0 to W. And one more thing you should keep in mind is you can see even though I have used a shape for illustration purpose, right, intentionally this is made symmetrical about F is equal to 0, right? The spectrum is intentionally made symmetrical about F is equal to 0. So there is a reason why, because the message and carrier which we will be considering will be real valued. The spectrum of any real valued signal will be symmetric about F is equal to 0, right? So this is baseband and symmetric about F is equal to 0. This is the spectrum of the message signal or baseband information signal, right? And this is the spectrum of our modulated signal. So you can see what happens is the modulated signal spectrum is nothing but what the message signal spectrum is shifted or frequency translated to plus FC and minus FC, right? And you can see here in positive frequency part this right the negative part of the message spectrum is also visible here. So that we will discuss the significance of negative frequencies later. So this negative part becomes visible here now, right? So basically after modulation what happens is the frequency is getting translated. So we have discussed it in previous video, and the positive frequency content will appear as actually what, upper sideband. So this symmetric about FC. Now if you consider only this positive part, this is symmetric about FC, that is our carrier frequency, right? And the part which is greater than FC, we'll call it upper sideband, and the part which is towards the left of FC is lower sideband, and you can see both are symmetric. And if you inspect the spectrum of standard AM, you can see two impulses at plus FC and minus FC. That is nothing but what that corresponds to carrier. So what we should understand is, in standard AM, right, we are transmitting the carrier also along with the modulated signal. Maybe that is the reason this is the simplest. But what you have to keep in mind is this carrier as such, it do not actually what, carry any information. So whatever power we spend for carrier, it is wasteful, right? That is one thing which you have to keep in mind, right? And one more thing, this upper sideband and lower sideband, if you see, it is symmetric about FC, and this upper sideband and lower sideband components of frequencies carry same information. It is actually what, redundant. If I know upper sideband, I can easily find out what is lower sideband, or the same information is there in the lower sideband also, right? So this bandwidth also, it's not effectively utilized. We are transmitting somewhat redundant frequencies, right? So that is the problem with standard AM, right? The problem with standard AM is power wastage. Why? Because we have a significant carrier component. Carrier is also transmitted. It doesn't carry any information. So that power is actually what, wastage. And the bandwidth, if you see, bandwidth is actually what, the range of frequencies. So it is ranging from FC minus W to FC plus W. So the bandwidth is 2W, right? But we know any one of the sidebands would have been more than sufficient, but we are transmitting actually what, redundant frequency. So the bandwidth is also not efficient. So we have such issues. If simplicity is the most important requirement, we can straight away go for standard AM. But if simplicity is not the important requirement, if we have stringent requirements of power or bandwidth, we'll have to go for other modulation schemes under AM itself. So for that's why we have double sideband with suppressed carrier. So what happens is, in DSBSC or double sideband suppressed carrier, this carrier part is suppressed. From standard AM, like instead of sending carrier along with the modulated signal, that carrier part is suppressed, so that power can be saved. So carrier part is suppressed, so power is reduced. But here also you can see we are sending both USB and LSB, upper sideband and lower sideband, both are being transmitted. So the bandwidth again is 2W. So it is not bandwidth efficient. Even compared to standard AM, the double sideband suppressed carrier AM can save the power of carrier, but bandwidth is not efficient. So maybe what can we do to reduce the bandwidth? So I told we need only this part. In fact, we need only this part. So how to extract only this part from the signal? So it's very simple. You have studied about band pass filter. So if you have a filter which transmits from FC to FC plus W and eliminates all other frequency contents, if you transmit the signal through a band pass filter like this, we will be able to get only one sideband. But the problem is, can we realize an ideal band pass filter like this? Is it possible to realize an ideal band pass filter? No. In normal filters, if you see, the normal filter will have some finite roll off, right? So it is not easy to realize ideal band pass filter like this. So that is one issue. But luckily, in some signals like voice signal, if you see, the spectra of voice signal will be like this. So you can see, this is in this we have some energy gap. So over this frequency range there is no energy, or in voice signal, say 0 to 300 Hertz, we have a null, right? There is no frequency content from 0 to 300 hertz in our voice. So in that case, what we can do is we can use a practical filter, right, to obtain only upper sideband or lower sideband. So in this case, I have shown only upper sideband, only one sideband, right? So instead of this, we can transmit only lower sideband. So this is possible because our information is of this form. Information has an energy gap around DC. That is why this is possible. So in single sideband, right, the bandwidth is less than W, and power is also reduced because we don't have carrier and also one sideband. So power is also further reduced, right? So that is about single sideband. And but this SSB transmission won't be possible in all information, but in some informations there will be significant DC component. In that case, we can't use a practical bandpass filter. If you use practical bandpass filter, what will happen is the content near DC will be attenuated, and that will lead to information loss. So we can't do that. So for that, we have another option that is called vestigial sideband modulation or VSB modulation. This is used in actually what video transmission in TV systems and all. So in video, we will have significant DC component. So if we use a filter, right, which will allow entire upper sideband and a part of lower sideband, it can have a transition region within this lower sideband region, or the other way around, it can transmit entire lower sideband and a part of upper sideband. So one sideband is fully transmitted and the other sideband is partly suppressed. So this is called actually what vestigial sideband modulation. Here again, we don't have any carrier, right? So, and also as one sideband is partly suppressed, the bandwidth will be between W and 2W, right? And the power also will be saved. So that is about vestigial sideband modulation. So that why I discuss this is, if you need to analyze any modulation techniques in terms of power or bandwidth, I need to obtain its spectrum, right? So how to obtain its spectrum? So to obtain its spectrum, first I should write the time domain equation or mathematical model of the modulated signal. Then I have to take Fourier transform of that. Then only I will be able to obtain its spectrum and do an analysis like this. So if we have to do that, we should mathematically model the other systems. So that's why in the forthcoming sessions, for all these modulation schemes, we'll be studying the mathematical model. We'll obtain its spectrum and we'll analyze what are the frequency contents present, what is the bandwidth, what is the power level, and all those aspects, right? And apart from that, we will also try and study some of the practical modulation and demodulation techniques. So that is what we'll be discussing in this particular module, and also in next module it will be about FM, right? So I hope the motivation behind why we are learning this mathematical model and why we should take Fourier transform. So you should not think why we are learning that, right? So that is motivation is clear, I hope. So from this, what you have to keep in mind is we have so these are what we have to study in this particular module. So you don't have to get scared by seeing the spectrum straight away. We'll from basics actually what we'll try and obtain the spectrums, right? So if you have any doubt regarding the Fourier transformation or obtaining spectrum, we will discuss those things. You don't have to bother. So I just told this now so that you will have an overall picture. You will be able to appreciate what we are going to learn next, right? So, and one more thing which I have to remind you is all these shapes of spectra which is used in this particular slide, it is only for illustration, right? So it is not compulsory that spectra should be of this shape. It can take any shape, but one thing which you have to keep in mind, as the signals which we are considering are real value, the spectrum will be symmetric about f is equal to 0, right? So then now we'll try and model the standard AM, right? So first we should know how to represent carrier. So our carrier is a sinusoid with frequency FC, right? So to represent that carrier, we'll use AC cos 2 pi FCT. So our carrier will be AC cos 2 pi FCT, and for simplicity we are assuming the initial phase phi of the carrier to be equal to 0, and in this particular figure, in this particular image only, and for the next illustration, using GeoGebra, I will assume AC is equal to unity, amplitude of is carrier to be equal to unity. So AC is nothing but what? A subscript C is amplitude of carrier, F subscript C is frequency of the carrier. And if you see, it has only one frequency content, so if you plot its spectra, it will be something like this. You don't have to like worry if you don't remember the aspects of spectrum and all, right? It will have a component at FC and minus FC, right? So this is how the spectra of carrier will look like. It has only one frequency content, right? So then we have a message signal. As I told, message signal will be baseband or band limited. So the spectrum will be a symmetrical baseband spectrum. It will have a maximum frequency content W and minimum frequency content 0. It is baseband, and it will also have actually what? Negative frequency. So the bandwidth or maximum frequency content of this message, we will assume it to be W. And one more thing which we will assume is this carrier frequency should be much greater compared to this W. Then only this modulation will give its benefits, right? And this carrier and message, they are totally independent. They are not actually what correlated in any manner. That is again an assumption, right? So now the modulated signal, as per the definition, the modulated signal, right, its carrier's amplitude should vary linearly according to the message, and it should vary around a mean value. So keeping that definition in mind, now I am going to write the mathematical equation for the modulated signal in standard AM. It is AC into 1 plus Ka m of t. This K subscript A, that is actually what? It's a constant called amplitude sensitivity. We'll see what is that in detail. Cos 2 pi FCT. So this is the equation for standard AM. So it is AC into 1 plus Km of t. AC cos 2 pi FCT is the carrier, right? And this 1 plus Km of t, right? This is called actually what? Envelope. This 1 plus Km of t is called envelope. And this Ka, it is called the amplitude sensitivity of the modulator. So if you are assuming a modulator as a system which will take message and carrier as input, then this Ka or amplitude sensitivity is some gain or attenuation provided for this m of t. So you don't we'll discuss that in detail further. So now we'll concentrate on mathematical modeling. And this absolute maximum value, what do you mean by absolute maximum value? It is actually what? If you take mode of it, or magnitude, maximum value of magnitude of this, right, that multiplied by 100 is called percentage modulation or modulation index. So we'll, in next video, we'll discuss more in detail about modulation index. But now for definition, just keep in mind the absolute maximum value of K and m of t is called actually what? Percentage modulation or modulation index. So this is the mathematical model of standard AM. So of course I will post one more video after this, which will be a simulation of this mathematical model with the help of GeoGebra. So then you will be able to appreciate how this modulation works exactly, right? But for instance, we'll consider this, and I have shown two modulated waves. One is actually, in one case you can see this is right, envelope is clearly defined and it has a one-to-one correspondence with the message signal. It varies exactly according to the message signal. But in the other case, right, you can see the envelope, it is actually what? Distorted. At this place there is some actually what? Phase reversals for the carrier, right? So the basic idea is, what you have to keep in mind is, if you are multiplying a sinusoid with a positive number greater than 1, it will be amplified, right? If you multiply a sinusoid with a positive number greater than 1, it will be amplified, right? And if you multiply it with a positive number which is less than 1, which is between 0 and 1, it will be attenuated. If you multiply a sinusoid with a negative number, what will happen? Its phase will be reversed, right? if it is multiplied with a negative number, its phase will be reversed. So that is what is happening here. So we'll analyze it in detail during the simulation which I mentioned, right? So this is happening because of this k, the ka into m of t, right? So if ka into m of t is mod of k into m of t is less than 1 for all t, then we'll get a perfect envelope, and it is easy for us to extract this envelope. But if k into m of t is greater than 1 for some value, or this 1 plus k into m of t, this entire thing, if it is less than 0, what happens is the phase of the carrier will be reversed. So at that point, what happens is actually what the envelope will be distorted. So we'll call it actually what, over modulation. So now we'll see the envelope S of t has essentially the same shape as the baseband signal m of t, provided the two requirements are satisfied. One of them is actually what, this mod of ka into m of t, mod of k into m of t should be less than 1, or 1 plus k into m of t should always be greater than 0. If it is less than 0, right, over modulation happens. So this 1 plus k into m of t should always be greater than 0. And one more thing is, the carrier frequency should be much higher compared to the maximum frequency content in message. Otherwise what will happen is, like you can see, the envelope won't be visualized correctly. This in detail we'll discuss when we discuss the spectrum of AM signal. So to start with, I want people to be comfortable with these terminologies and with these mathematical equations which we have written. So in forthcoming videos, what we will do is we'll take spectrum of this and analyze this in detail, and also we'll analyze the effect of Ka or Ka and m of t as such, right? So now this is how we can time model a standard AM signal in time domain. So you should remember this, right? And this is normal modulation. This is easy to recover, and this is actually what, distorted modulation or over modulation, where envelope is distorted because of phase reversal of carrier wave, and it happens because of mod of k and m of t is greater than 1 for some time. It's exactly k and m of t is negative, because of that, like, or greater than less than -1, because of that it happens. Maybe we'll discuss that in detail, right? For instance, maybe we'll stop the discussion here, and I'll also show a figure with actually what, percentage modulation. So this percentage modulation, Ka into m of t, right, this Ka into m of t, that mode of Ka into m of t, it's maximum, right? So what is percentage modulation? Maximum of mode of Ka into m of t. If it is equal to 0.5, you can see a very clearly defined envelope. There is no actually what, distortion. So in this case, the message is considered to be a low frequency sinusoid. But if this maximum of mode of Ka into m of t, if this is equal to 1, that is 100% modulation, you can see it almost actually what, touches 0, but even then envelope is actually what, clearly defined. And also you can see the depth of modulation is also increasing. Here depth is less. As percentage modulation increases, depth of modulation is increasing. But this is the case where we can actually what, exactly extract the envelope from this. But if modulation, if max of Ka into m of t, that is percentage of modulation, it is greater than 1, or it is 150, you can see this is the envelope, but we can't obtain that. Now envelope is distorted because of this phase reversal, right? So now the envelope is, you can see now the envelope is something like this, that it is not actually what, in correspondence with the message. Of course actually the envelope maybe with very complicated receivers we can extract the envelope, but right, it is not simple as like standard AM with modulation index less than 0.5. So this is what happens. And a detailed um, simulation, GeoGebra simulation, I'll post today evening or tomorrow itself, right? And maybe the upcoming sessions, upcoming videos also I'll post, so that during our live sessions we can have more simulations and all those discussions, right? So for instance, today we have only this much. So what we have learned today is we have seen the definitions of AM, and we have seen different cases of AM and what is the motivation behind actually what finding out mathematical model or finding spectra, and how bandwidth and power efficiency is different in different AM schemes, right? And we have even seen some of the basic terminologies related to mathematical modeling of standard AM. So we will end the session here, right? And in next session we'll continue from this point, and we'll see the spectrum of AM and standard AM generation and detection. So thank you so much.